Imagine unlocking a whole new world of materials that could revolutionize quantum computing hardware. But here's where it gets controversial. For years, many promising superconducting materials, like transition metal nitrides, carbides, and silicides, have been nearly impossible to shape into functional quantum devices using the usual chemical methods. This limitation has kept their potential locked away. Until now, researchers have introduced a groundbreaking fabrication technique that breaks through this barrier, allowing scientists to explore a much wider variety of superconducting materials for quantum technology. Their findings, recently published in Applied Physics Letters, showcase how physical patterning methods, particularly a process called low-energy ion beam etching, IBE, can successfully create high-quality quantum devices from these challenging materials. Led by Professor David Shargerty at NYU Tandon, the team proved that this alternative approach works just as well as traditional chemistry-based fabrication. To demonstrate this, they used niobium, a superconductor already well understood by scientists. The devices they built using the IBE method matched the top-tier performance of those produced by the conventional chemical processes, offering a promising new path to develop more diverse and potentially superior quantum hardware. Why is this so important? Quantum computers promise to solve certain problems that traditional computers simply can't handle, such as discovering new medicines, cracking complex encryption codes, and optimizing financial models in unprecedented ways. But to make these ambitious goals a reality, quantum devices need components that keep delicate quantum states stable long enough to perform complicated operations without error. Achieving this requires building incredibly precise and reliable hardware to minimize errors and enhance quantum systems' fault tolerance, Shargerty explained. This new fabrication method widens the scope of materials available, offering fresh opportunities to improve the durability and performance of quantum components. Dr. Matthew LaHaye, a researcher at the Air Force Research Laboratory and a collaborator on the project, noted, "Using material-agnostic fabrication techniques like this one dramatically broadens the design options for quantum hardware. By tapping into materials that have been largely overlooked, we could significantly accelerate the development and scale of quantum computing technologies." The process to test this innovation involved PhD students Miguel Manzo Perez and Moed Jamalzadeh, who co-led the study. They designed superconducting resonators, key components for quantum circuits, and developed fabrication steps combining electron beam lithography with IBE. This intricate work was performed at NYU's Nanofabrication Cleanroom, the first of its kind in Brooklyn dedicated to advanced quantum material research. Shargerty, the Cleanroom's first faculty director, highlighted its role. NYU NanoFab features cutting-edge equipment and a focused mission to support the creation of next-generation quantum and superconductor devices. Besides pushing academic frontiers, it acts as the prototyping center for the Northeast Regional Defense Technology Hub, facilitating the transition of superconducting quantum technology from the laboratory to practical applications. After fabrication, the team sent their quantum resonators to the Air Force Research Laboratory. There, contractors Christopher Nadeau and Man Gwen tested the devices at temperatures close to absolute zero, the extreme cold necessary for quantum superconductors to perform. The results were impressive. The resonators showed very low loss, which indicates minimal energy leakage and high device quality. This low loss is critical because it reflects how well a superconducting device can maintain quantum coherence, essential for error-resistant quantum computing. The success of the IBE-based fabrication proves it's a viable way to build low-loss quantum hardware without relying solely on conventional chemical techniques. This breakthrough not only expands the toolkit for quantum device engineers, but also invites an important question. Could tapping into unconventional materials via physical patterning methods finally unlock the scalability and robustness that quantum computers desperately need? Or are there hidden challenges yet to emerge as this approach is applied to more complex materials and devices. We'd love to hear your opinions. Do you see this as a transformational leap for quantum hardware? Or is the jury still out? Tell us what you think in the comments. For those interested, the detailed study is titled Physical Patterning of High-Q Superconducting Niobium Resonators via Ion Beam Etching, published in Applied Physics Letters in 2025. In summary, this new fabrication technique represents a significant stride toward diversifying the materials available for quantum hardware and improving the performance potential of future quantum systems. By stepping beyond traditional chemistry-based methods, researchers are opening doors to innovations that could accelerate the quantum computing revolution.